Good day and welcome back for part 2 of our discussion on the mean value theorem. In our previous video, we introduced Rolle's theorem, investigated it graphically, and worked through an interesting example. In this video, I'd purely like to introduce the mean value theorem, note kind of the connection back to Rolle's theorem that we discussed previously, and interpret it geometrically. I will save a few applications or examples involving the mean value theorem for the third and final video in this section. The statement of the mean value theorem, which I will almost always abbreviate with MVT, is very similar to Rolle's theorem. We start off with assuming that f is a function that satisfies, and now just two properties, but they hopefully look familiar. The first is that f is continuous on the closed interval from a to b. The second, as you might have guessed, is that f is differentiable on the open interval from a to b. And if this is the case, we are guaranteed that there is a number c somewhere between a and b such that f prime of c is equal to f of b minus f of a, all divided by b minus a. And before diving into the geometric interpretation of the mean value theorem, let me just make the connection back to Rolle's theorem. So if we recall from our previous discussion on Rolle's theorem, we had those same first two hypotheses that must be satisfied. But there was also a third hypothesis that was f of a is equal to f of b. And the conclusion of Rolle's theorem was that there is some value c between a and b where f of c is equal to 0. And note, if f of a and f of b are equal to each other in the mean value theorem, f prime of c is equal to 0. So Rolle's theorem that we previously discussed is just a special case of the mean value theorem. And by special case, I really just mean it's a particular instance of the mean value theorem. It's that particular instance when f of a equals f of b. I would also like to note before talking about the geometric consequences is that similar to Rolle's theorem and the intermediate value theorem, before using the mean value theorem, you always need to verify or state that the hypotheses are satisfied. And typically, this is not a difficult part of the problem, but it's more just based upon the function we're dealing with, stating because it's a polynomial or because it's a trig function, something is true. Let's now explore what the mean value theorem is telling us from more of a graphical, or we might think geometric perspective. So we have a function which is continuous and differentiable, and I'm going to indicate points corresponding to a and b. So we would have a point a f of a and b f of b. And if I think of connecting those 2 points with a continuous differentiable function, so I can draw it without lifting up my writing utensil, there's no sharp points or cusps on the graph. What we are guaranteed by the mean value theorem is this point in between, c, with f prime of c equaling this quantity, f of b minus f of a over b minus a. And what I want you to think about for a moment is this quantity, f of b minus f of a over b minus a. How does that relate to the 2 points, b f of b and a f of a? Notice if we think about the line connecting those 2 points, what would the slope of that line be? Exactly. The slope of the line from AF of A to BF of B is rise over run. And this f of b minus f of a over b minus a is precisely that quantity that appears in the conclusion of the mean value theorem. And note, if we want to see this c value graphically in our picture, it's really asking, when will the tangent line to this blue curve be parallel to this red dashed line connecting those 2 points? And by inspection, we can see that it appears maybe approximately at this point on the graph. When you draw the tangent line and the red dashed line appear to be parallel to each other. So this would be the value C that we are searching for. So in words, let's just note what the mean value theorem is telling us. So there is a C value in between A and B with the slope of the tangent line at that point equal to the slope of what we previously called on our first day of class the secant line connecting those 2 points AF of A and BF of B. And let me go ahead and make a similar observation that we made for Rolle's theorem. It's what we call in mathematics an existence theorem. It tells us there is at least one such C value in between A and B where something happens. It does not tell us how many of those C values there are, except for at least one. And it doesn't tell us, where they are located. So it is perfectly reasonable that we could have more than one such point. So let me draw one more picture to kind of finish up our discussion. So if I go ahead and connect the points AF of A and BF of B with a nice continuous differentiable function, it's reasonable that maybe I can make it look a bit different than previously. And now when we search for points on that curve where the slope of the tangent line is parallel to the secant line I have in red, 2 spots jump out to us. We have 1 and 2 such tangent lines. And those tangent lines are going to correspond to these inputs, say C1 and C2. So it is very reasonable that there will be more than one such point. And this finishes up our discussion / introduction into the statement of the mean value theorem along with its geometric interpretation. In our next video, we'll dive into several examples that require us to use this mean value theorem. So stay tuned and take care.